Question 6. Figure 6.1 shows the synthesis of this lidocaine. This one. And part A. W can be formed by reacting the HOCH2COOH with excess SOCl2. So the W is the first reactant which react with X to form the Y, and after that Y will form the lidocaine. So this is the W is a compound with two groups, acyl chloride and this haloalkane. So this one can be formed when we use this compound with SOCl2. Okay, so first you need to recall back what you learned in AS, which is this reaction. Alcohol, when reacts with SOCl2, the OH will substitute by the chlorine, so it will form halogenol-alkane. So in A2, what you learn is when a carboxylic acid reacts with SOCl2, the OH in this carboxylic acid will substitute by the chlorines, and eventually it will form this acyl chloride. So means this compound has two groups, the hydroxyl and carboxylic acid. So therefore we know that it will be two substitution, means this one will change, this OH will substitute by a chlorine, and this OH will also substitute by the chlorine to form these two functional group, right? And remember to balance equation, because two groups involved and both reacts with SOCl2, so eventually it will form 2 moles of SO2 and 2 moles of HCl. Part B. After W and X have reacted together and excess this CH3CONA, sodium ethanoate, is added to the reaction mixture, suggest why. So first, you need to at least know what is the reactions between W and X. So, okay, I bring this X to this side, right? So you can see how they react. So because in the X it has a phenylamine here, so these phenylamines will react with the acyl chlorides here. So means it will undergo a condensation reaction. So the H in the amine and the Cl in this acyl chloride will combine and form HCl. And of course, it will form a new bonds between the carbonyl group and the N to form amine. So it will form these amine groups. So means after W and X reacts, it will form this amide, and at the same time it will form a byproduct HCl. So the reason why it needs to use this salt, okay, because when we add this salt, so this anion, so this carboxylate, it will react with the H plus, means the H plus from the HCl just now, right? Because the mixture now is acidic, we want to remove the H plus, so therefore we add the salt there. So the salt react with H plus from the acid. So the purpose is very direct. So it's to remove excess H plus that produced. Okay, part C. The reactions of W with X in the reaction 1 follows addition-elimination mechanism. So when you see addition-elimination, means it's the reactions between the nucleophile with the acyl carbon here, not the carbon with the chlorine here. So it must be the acyl carbon, this one. So what you need to do is first put the lone pair on this nitrogen, because this is a nucleophile. So, and draw one arrow from this lone pair, point to this acyl carbon. And of course, this acyl carbon, you need to put partial positive. Oxygen, you put partial negative. So because of this partial positive, so this nucleophile will get attracted to this acyl carbon. After that, you need to draw another arrow from the double bond to the oxygen to show that pi bonds break, and this pair of electrons will move to oxygens, and after that it will form this intermediate. So this intermediate, you need to draw a charge positive on the nitrogen, because the nitrogen donates a lone pair to the carbon. It's kind of like electron deficient. So put a charge positive, not partial positive, charge positive on nitrogen. And of course, you need to draw these oxides, means oxygens with the negative charge and lone pair. So the intermediates must correct because it's 1 mark. And again, because the instruction already given, you can use AR to represent the groups that bond to the amine in the X. So therefore you just put AR here, so it's easier. Another thing you need to do is you need to draw the 3 arrows. Okay, so first is the arrow from the lone pair on the oxide, point back to the CO bond to show that the pi bonds reform. So at the same time, the CCl bond break. So just draw 1 arrow from the bond, point to the chlorine. Another bond you need to, another arrow you need to draw is from one of the NH bond. So draw 1 arrow from the bonding, point to nitrogen to show that the lone pair restore. So what happened now? Which species now being removed? So it's the chloride and the hydrogen ion. So these two will combine and form the HCl. Okay, of course, after the reaction, it will form the amide. So means this one. Means this one, the Y. Right, so this is the AR group just now. Okay, so that's the mechanism, and you must at least know how to draw all these partial positive, lone pair, and these arrows. Okay, part D. So this amine, okay, reacts with the Y in reaction 2. Explain why this compound can act as a nucleophile. So it's very easy. Nucleophile is the one that electron rich, especially it has a lone pair. So because the nitrogen here has a lone pair, and this lone pair able to donate to others, so therefore this amine always can act as a nucleophile. So that's the reason why it is a nucleophile. Okay. The N in the compound can donate its lone pair to the others. That's why this one always can be a nucleophile. Part E. The purity of lidocaine can be checked using thin layer chromatography. So first you need to know the material that used in this thin layer chromatography. So normally we will use the glass plate which coated with the oxide, aluminum oxide or the silicon oxide. So this is how it looks like. So this is a glass plate, and you see the white color here. So this is the oxide that coated on the surface. So this will use as the stationary phase in this TLC. So the mobile phase will be the solvent used, which is the ester. So this ester will bring the solute go up during the separation. If something look like this, we put the TLC plate, means this plate, into this chamber, and we put the ester inside the solvent, and of course the glass plate itself, before we put into this chamber, we must spot the sample on the plate. So let's say we spot here, right? So after that, we'll let these separations happen. The solvent, the ethyl ethanoate, will goes up, slowly goes up. When it goes up, it will bring the solute or the sample together. So this in this question, there are two compounds, X and the lidocaine. So as you can see from this retention this factor or this RF value, so is 0.49 for this X and 0.71 for this lidocaine. So we know that the affinity of the lidocaine to this solvent is more. Later I tell you why. So the separation is something like this. The mobile phase will goes up until it's reached this line. Normally we'll draw a line here, or we will let the solvent reach certain level. So after that, we'll take out the whole plate, and the distance that travel by the solvent we call solvent front. So this is the total distance that travel by the solvent. Then we need to use this one for the RF calculation. Okay, later we'll discuss that. Now for part 1, identify the substance that's used as the mobile phase and stationary phase in this TLC. Okay, mobile phase is the one that bring the sample goes up, so it's the ethyl ethanoate. The stationary phase is what I told you, is the oxide. You can put either one, this SiO2 or the Al2O3. So, and these oxide, again, they are the one that coated on the glass plate. Now, part 2, describe how the RF value can be calculated. So we need to get two distance. Okay, of course, first we need to get the distance for the solvent. So the solvent front. So this is the total distance that travel by the solvent, and we need to get another one. Let's say the distance that travel by the lidocaine, let's say is here. So means we get this distance, right? So once we get the distance, we need to use this compare with the solvent front. Means the distance traveled by the solute over the distance traveled by the solvent. So we will get the RF value. From here, you will know that the RF value is actually will mostly less than 1, because max is can go is 1, right? So this is how we calculate. So from here, we know that again from the values, because the RF value for X is 0.49, which is lesser than the lidocaine. So means it's somewhere here, right? Just example. So means it's lower than the lidocaine. Means the mobile phase, this ester, not really able to bring this X goes up. Means the affinity of this X towards this ester is lesser. The lidocaine has higher affinity towards the ester. That's the meaning. From the value we know what is the affinity, how well it can bring by the mobile phase, right? So therefore, for part 3, if you understand what I say, for part 3, you know what is the correct answer. Suggest why the RF value of X is less than the lidocaine. Because the X has more affinity towards stationary phase. Or you can actually say that because the lidocaine able to dissolve better in the solvent, therefore it can bring further by the solvent. That's how you explained. Part F. So this is the Proton NMR. So first, I roughly discuss this NMR spectrum, Proton NMR spectrum, with the structure, so you can understand the question easier. Now let's start with this ethyl group. As you can see, is the N, okay, with this 2 ethyl group. So I did some modification, so I just cut it and I put 2 ethyl group, so you can see that clearly, right? So let's start with this CH3. This CH3 and this CH3, they are equivalent. So they are actually one group. When we want to know the splitting of this CH3, so this is the one group and is coupled with the proton on adjacent carbon, which is these 2 proton. So it's 1 plus 2, so you get 3 peaks. So means you get triplets. So the triplets here, as you can see here, 1.1, it's from these two CH3. And how about the others? So let's look at this CH2. This CH2 and this CH2, they are equivalent. So this one as the one group, so it will couple with this and this and this proton. So it's 1 plus 3. So this will give you a quartet. So the quartet here, you see there's 4 peaks here, these signals at this 2.6 ppm. So is generated from by this CH2. So, and after that, okay, let's look at this one. It's easier. So when you see a multiplets, many peaks around 6 point something 7, so it's telling you is the protons in the benzene ring, right? So it's here, right? This one. And as you can see here, there is a amide group here. The protons that in the amide group, it will be a singlet, and is around 9 ppm. So if you wonder why it has this 9 ppm, so you can actually check here. So amide, as you can see, this one. Whenever there is amide, you see a peak or a signal, right, around this, within this range. Now, this one okay, this one okay. So the triplets okay. Now this one no problem, quartet. So we need to know what is the proton that will form these 2 signals. Okay, this one, 3 ppm and 2.3 ppm. So before we continue, let's go to the parts that Okay, that is specified the area. Okay, in part 2 is already mentioned the relative peak area of the peaks at 3 and 2.3 is 1 to 3. 3 and 2.3, they are 1 to 3, means the protons ratio will be 1 to 3. So means this one is 1, this one is 3. So they are 1 to 3 ratio. Now, for this one, the signal at 3 ppm is from this CH2. Why? Because this proton, this CH2, is next to a carbonyl group. So whenever a CH2 or CH3 next to the carbonyl group, so its chemical shift is 2.2 to 3. So it is here, this one. So therefore, we are quite sure that it's the CH2 that next to the carbonyl. So that's why this one, this singlet, is from this CH2. So this is how you get it. And from there, we actually know this. Okay, from here, the last one is actually this one, the CH2, CH2. So the 2.3 is the one that next to the benzene ring. So this one we can actually get from this alkyl next to aromatic ring, so which is 2.3 to 3. So how and why we know it is from this these two methyl group that bond to the benzene ring? Because here it has 3 proton, here also has 3 proton, and this CH2 just 2 proton, right? So therefore, we know that their ratio is actually 1 to 3. 1 to 3. So because this one is okay, this one is 2, right? 2. So this one is total 6. So therefore, it's 1 to 3 ratio. So we are quite sure that the signal at 2.3 ppm belongs to these 2 methyl group, right? And this signal at 3 ppm is from this CH2. So this is how we get all the signals. Of course, in the question, it is not going to ask you all of that, but I try to discuss all this with you so you can have a better understanding, right? So now let's continue. What is the questions needed? Part 1. Name the splitting at 2.6 and 1.1 ppm. So now 2.6 is here. 2.6, as I told you just now, the quartet, right? So this is the 2.6. The splitting, one signal, it has 4 peaks, so this we call quartet. 1.1, this signal has 3 peaks, so we call triplets. So that's how you name that. Okay, part 2. The relative area of the peaks at 3 and 2.3 is 1 to 3, already discussed just now. Identify the protons in this Proton NMR of the lidocaine that are responsible for the peaks at the following chemical shift. I already told you just now, isn't it? So around 7 is the multiplet here, around 7 is from the protons in the benzene ring. So how you actually name that? Very easy. You just get the name from these tables, right? So this one. So you just need to write this one. Environment of proton. So attached to aromatic ring. That's the answer, right? So that's why you get this. Attached to aromatic ring. So the chemical shift 3.0, again, 3.0 is this one. 3.0 is this one. So it's the CH2 that bond to the carbonyl group, right? So you can just put this one, alkyl next to carbonyl. So that's why you get this name, alkyl next to carbonyl. 2.3 is the alkyl next to aromatic ring, which is this one, already discussed with you. So 2.3 is here, this one, the alkyl group that, this one, the 2.3, alkyl group that bonded to aromatic ring. So you just, this one, okay, alkyl group next to aromatic ring. So you just put the answers here, right? That's all. Okay, last part. Predict the number of peaks in the carbon-13 NMR for the light token. So this is the structure. First, you need to know how many equivalence carbons there. So because this part is actually symmetry, so this carbon and this carbon, they are equivalent. This carbon and this carbon, they are equivalent. This one also equivalent. So therefore, they will not really form double, means more different signal. They will form a same signal, right? Okay, so now let's start from the right hand side here. So because here there are two ethyl groups, but these ethyl groups, they are equivalent. So in there it has two carbon, so it will give two signals. So 1, 2, 3, 4, 5, 6, 7, 8, 9. So you see total 9 peaks there, right, in this carbon-13 NMR. Okay, that's all. Thank you.